share the screen and presentation mode.
Looks good.
Okay, so as Brian was saying, in this session, we will show 3 examples of analysis because there have been a lot of theory, a lot of blah, blah, blah in the previous sessions. But to show you really what we do with this methodology and with these tools. In my case, I'm going to talk about the set of BSc performance tools. As I said, we have the execution, a platform, a code, and an input. And then we have the tool that is called extract, that is the tracing tool. With extract, we obtain a trace. With another tool that is called basic analysis, we are able to obtain the metrics automatically. So you feed the traces to this script and you get the POP performance metrics. And then with Paraver, you can visualize the traces. We also have another metric that it's called another tool that it's called TALP, and TALP only gets you from the execution. It gets you directly the metrics. This is what one new tool that we have in the project because of what we were commenting before, that at the end traces are getting bigger and bigger. So we need this kind of intermediate tools that will allow us to get the metrics without all the tracing information, and then we are able to decide which part of the code it's interesting to measure. Additionally, that I'm not going to present today, but we also have it, we can obtain for GPU executions an NVIDIA Inside System Trace, and we have another tool that is called NCC to PRV that will translate this Inside Trace into a PRV, into a Paraver trace, and this will allow us to visualize this NVIDIA Inside Trace with Paraver. And use all the capabilities of analysis of Paraver in this kind of traces. Today, I'm going to present an example that uses TALP, extract, and Paraver. I'm not going to cover all the other tools, but as I said, we have other advanced trainings, if you are interested, where we explain more tools. So in this case, I'm gonna talk about one analysis that we did. This is one of the biggest analyses that we have done in POP. It was, if I'm not mistaken, 1,000 Mare Nostrum 5 nodes. Each node of Mare Nostrum 5 has 112 cores. So it was a very big execution. This code is a Plasma code, and it's parallelized with MPI and OpenMP. For this reason, because it's a big execution, we started doing the analysis with TALP. So the first thing that we did was to obtain the metrics that I was explaining before, the metrics with TALP. Now you can see that before I only explained the MPI metrics, now we have also OpenMP metrics here. And as I was saying before, we see the value of IPC, the frequency, and the elapsed time. So we also have these numbers that also allow us to see if there's something that is not going completely well with them, or that we need to check something. With this table, what we saw is that there's an issue in the parallel efficiency of this code. We don't see anything very relevant in the computation part, so we don't see anything in the scalability because we just have one run, but if we check the global numbers, they look quite okay. But we saw that for this part of the code, there was an issue. We only have the metrics because we are using TALP, but with this information is when we decide with extract to obtain a trace, but a partial trace. So this would be like the global execution, the full execution, where you have the initialization. In this case, the code colors are the different regions, the different functions that were given to us by the customer. And we see that there's an initialization, and then there's this region here that iterates 3 times. And this one was the one that we were obtaining the metrics for. So what we did is we enabled the trace only for this part. This is the view that is telling us which tracing region is enabled. Now we have the trace only for this part. We are able to visualize it and check the structure, what we were seeing before. This is the structure of that small part. We see that there's a long part that it's the spatial space, this blue. Then we have the propagate fields, which is this part here, the velocity space here, and the update system here. And we are able to see how much time of the iteration each one of these regions represent. So the idea is to give you just an overview, so I won't explain the whole analysis that we did for this application, because in this case, for example, we analyzed this region here that we see a pattern that there's a lot of communication here, a lot of load imbalance here, and we can analyze this one because it's representative of these 3 iterations that are inside this region here. We have 3 iterations that look the same. But today I will focus only in this part here. So now we say, okay, I want to focus on the propagate fields region, this one here. Just because today I'm presenting this, we did the analysis for that, because you may ask why you don't focus on this, because I think it's more interesting the findings to show in this one. So now again, we get the metrics for the propagate fields region only for that small part that I was mentioning before. And what we see is that the main issues are the MPI load imbalance. We see that there's a very low value, and the OpenMP load balance, the OpenMP serialization value that is very low also. So we have 2 metrics that they are very low, and those are the ones that we are going to analyze. So now we open the trace knowing that what we want to look for is MPI load imbalance and OpenMP serializations. We open the trace, the region of the trace of that small region that I was focusing now, and we focus in this part here. If we focus in this part here, you will see that we are doing zoom in, zoom in, zoom in, and it's a bit what I was saying before. So we go from the global metrics, the global overview, and then we start zooming in until having a lot of detail. So we have this wide range of detail that we can check. So in this, we zoom in that part, and we see that there are some processes that are taking longer than others. So if we zoom in just some processes, because this execution was so big in the number of processes that it's difficult to see anything. So we zoom just in some processes. Now you see the same time, but only showing some of the processes. What we see is that some of the processes have more work than others. So here we have process 3302 that is computing, but the other process 3303 is not computing anything. So here we see the MPI load balance. One process is computing while the other not. In the next iteration, this process is computing, and this is computing a very small portion of time. So this we see that there's a MPI load imbalance. But we also see that this region that is causing this MPI load imbalance is not parallelized with OpenMP, because these 4, so I don't remember if I said this, but this application is MPI plus OpenMP, and we are running with 4 OpenMP threads, each process. So what we see here is that the OpenMP threads are not working. So the main thread is computing, but the work is not distributed among the OpenMP threads. So this is the reason for the OpenMP serialization. So this fact is giving us this OpenMP serialization. So now if we focus in this other part here, so the one that I was showing, it was here. Now we zoom in here to see what is happening in these iterations that look more or less the same. And we see this pattern. it's again a bit difficult to see anything with so many threads and processes. So we do again a zoom in some processes. If we zoom in, we see this pattern, which is like an arrow, but it's still difficult to see what's going on. So we zoom a bit more, and now we get this. So what are we seeing here? We are seeing several processes. Each process has its 4 threads. And in this window here, what you see is the OpenMP parallel region, when the OpenMP threads are inside an OpenMP parallel region. And if we zoom a bit more in only 2 of the processes, so we see here one process and here another one, what we see is that the green region is not well distributed among MPIs, because only this MPI is executing green. This one, it's not executing the green one. The purple, the same. It's not being executed. There's one process that is executing more than the others. But it's also not parallelized with OpenMP. So not parallelizing it with OpenMP means that we are making the load imbalance even worse, because the threads could help distribute this load, but they are not working either. If we check the blue and the red regions, what we see is there's load imbalance at the MPI level, because these 4 threads belong to one MPI process and these 4 belong to another. So this MPI process has much more work in the blue region than this one, and the same for the red one. So the red one, this process has much more work than this one. But there's also load imbalance at the OpenMP level, because in this process, all the threads are working the same, but for the top process, only one of the threads is working, while the others doesn't have work to do. So we were checking also in the number of useful instructions for this same view. We see that they are all executing the same number of instructions, these 4, but in this case only this one is executing instructions, and the same for these 2 that correspond to these regions here and here. So what we see from here is, okay, you have several problems in this code. You have the green and purple regions that have an issue with MPI load balance that comes from number of instructions, so the work is not well distributed. And on top of that, they are not parallelized with OpenMP. So OpenMP is not helping you alleviate that MPI load imbalance. And in the blue and red regions, what we see is that there's MPI load imbalance, because one process has more work than the others, but there's also an OpenMP load balance issue, because not all the threads are working the same for some of the processes. So this is a bit the example that I had prepared, so that you could see how with a very big run, with thousands of MPI processes and getting the metrics, we dig down, we zoom in, until we see details like these ones of very small regions, parallel regions, that are not parallelized efficiently to obtain the maximum efficiency of the code. And that's the example that I had prepared for the BSC tools. I lost again the controls of Zoom. So if Mark, if you can do again, stop my sharing, please. Thank you.
Okay, so we'll see more about Paravar and X-ray on the Friday presentations. We are a little bit ahead of time, which is good. Let me see if I go next and I can keep on time. Where do I want to be? Not in the agenda for sure. Okay. So the example that I chose was one that's using MPI and OpenMP plus the combination with CUDA. The tools that we develop in ULIC are under the collection Scholastica. So Scholastica is our trace-based analyzer. It's open source. It supports MPI, OpenMP, and various threading models. You'll hear more about this tomorrow, so I won't elaborate in any detail here. But the measurement system that is used for collecting measurements is ScoreP. That generates either profiles, traces, or the combination of both. Again, supporting the range of different parallel paradigms. And when it's generating profiles, it's generating them in a format which our Cube visualizer will present. The way in which the tools work together is that ScoreP is used for instrumentation and for coordinating the measurements. So when the application runs, we're collecting data for each event on each process and thread. We can aggregate that information together into a summary report, which we'll see in a moment, or we can configure our measurement in such a way that we generate execution traces, and then those traces are automatically analyzed to produce an augmented report. So the display we use is known as Cube because it has 3 dimensions to it. One dimension, which are the performance problems, the different metrics that we've collected, where in the program these occur, so which parts of which functions and parallel loops are being executed, and then which processes, threads, etc., is where the time or the metric is spent. So that's a very generic presentation that you can customize and adjust in various ways. Again, an open source utility. The example which I'm going to look at is a measurement which was done on a predecessor to our Jupyter supercomputer system. So it was an early set of nodes for Jupyter. These are the Grace Hopper GH200 superchip nodes. So they have ARM CPUs with 72 cores and then 4 NVIDIA GPUs per node. This test case is coming from one of the centers of excellence, and they provided a test case that they were interested in comparing the execution where it could run with different numbers of threads and compare the performance. We were able to use the information that the application provided in terms of regions which they had marked of particular interest. So those were the ones that we could capture and then use to structure the profiles and the traces that were collected. There was some mention about measurement overheads and dilation. In this case, we were seeing something around between 7 and 40%, which is quite high, but we were also seeing a lot of run-to-run variation from the application as well. And we believe that that was partially related to the early access nature of the system and the fact that there was, we believe, quite some interference from other activities on the system when measurements are taken. So as I mentioned, we have this Cube display which presents metrics in three columns. There's a lot of detail here which I won't go into detail, but we have metrics on the left-hand side. The ones which are selected here are the time-based metrics, where we can see the time broken down into what is computation or what's in various MPI activities, various CUDA activities, as well as what's happening on the GPU device. The other metrics are for things like the MPI bytes transferred or the number of times that various call paths, various kernels are executed. As I said, the application itself had information which gave us some structure that we could exploit. In this case, the time step loop was marked, and that's going to be our main focus of analysis, which we can look at. We can go down deeper into what's inside there, but at the moment, we're just going to look at the time step. The kernels which are executed from the time step are also listed here. Those are the kernels that are highlighted in the shading here. So there's lots of different computational kernels which are executed at different points of the time step loop. And on the right, we see not only the processes, which are the time in the various processes, but also the time for the various CUDA devices are used and what time is spent in the different CUDA streams of execution. So we can already get quite an overview of the fact that one of the streams is used much more than the others. There's one of the streams which we don't see being used at all, which is not a big problem. And we can, at this level, try to understand what's happening across the 32 nodes, the 128 GPUs here, but we already have quite a lot of information to present in this tree structure. So an alternative presentation is one where we present things in a topological presentation or a set of maps. So here we have the different streams, we have the CPU at the bottom. The color coding used here as well as in the other panels is from the lowest 0 up to the highest value here. And we can see that things are relatively balanced. All the colors look very similar. Everything's red for this stream, everything's pretty uniformly yellow-orange in this one at the bottom. But it depends, as we zoom in and we focus on different things, we could see that the colors change and help us identify where things might not be quite so well balanced. But as well as having that level of insight into all of these metrics and where there's load balance going on, one of the things that we have incorporated more recently as part of the POP Center of Excellence is the ability to summarize the efficiencies and present those. And so when we calculate things like the GPU efficiencies for our focus of analysis time step loop here, we see that the load balance efficiency is very good, close to perfect here. But when we're running on 128 GPUs, the efficiency for communication and coordination of the GPUs is much less good. So here we're down to 0.15. If I compare this execution, which was with 32 nodes, 128 GPUs, with a smaller scale run with just a single, with just 4 nodes and 16 GPUs, there the communication efficiency is much better. It's far from perfect, but it's much better, and we can see how that changes not only for different numbers of processes, but by selecting different focuses here, we can see how it varies for different parts of the application. Putting all that information together into a table allows us to see the trends more clearly. We see that the load balance efficiency stays very good all the way up from the smallest configuration here to the largest one, and its orchestration or communication efficiency for the GPU here, that's where the efficiencies are degrading very substantially. When we look at the efficiencies of the CPU side, there the efficiencies are low as well, but here the application developers weren't worried about keeping the CPUs busy. They wanted to make sure that the GPUs, which is where most of the computation is done, that they were kept busy throughout. But the fact that they were struggling with the orchestration efficiency meant that there were times where the overheads transferring data in and out of the GPU and starting lots of kernels were diminishing the execution efficiencies. The focus of analysis, as I said, we were using is this time step loop, but we can expand that to different levels, and then we'll see by expanding the tree selectively where inside that time step loop time is spent. Here we're taking it down through the pressure solve into HSMG solve, and then inside the HSMG solve is where we're seeing there's a parallel region where it's executing 2 computations in parallel, one which is a Schwarz computation, the other which is a coarse grid computation. And when we look at how those are executed, we can see that those are executed by different threads. And one of the threads is taking 1.5 seconds in each of the threads. The other thread is taking 2.5. So the coarse grid solve takes about 2.5 seconds. The Schwarz solve, part of the solve is 1.5. They could overlap those two together, and then you'd have some waiting time where it's not able to continue until the slower one catches up, and then the faster one can continue. So there is a small benefit here from using 2 threads. There's only 2 computations here, so they can only exploit 2 threads. But it was interesting that even when they were using 2 threads, the benefits were far from what they were really hoping for. So yes, there was a small benefit in the pressure solve, which is where this parallel region is, but there was actually degradation elsewhere. Looking at what's going on in more detail in the pressure solve, we see that both parts of the solver are actually doing very similar things. So they're both using MPI. They're both doing both point-to-point and collective communication for what they call gather-scatter communication between MPI processes. Also, both of these threads, both of these computations are executing CUDA kernels. They're using different streams for the CUDA kernels, but they're both executing on the same GPU. If we look at what's happening in a trace, again, we're down just to 4 processes here. So this is a single node, 4 processes, where we can see that we have a timeline at the top for each of the MPI processes, and then we can see where CUDA kernels are being executed on the CUDA streams. There are times when there's very little use of the GPU. The part at the beginning here is initialization, so that's a one-off cost, which we weren't too worried about. But even when we get into the time step loop, where it's doing, in this case, 300 time steps, we can see that there's a far from continuous utilization of the GPU devices. The graph at the bottom is showing the functions that are being executed. We could show a similar one, which would actually give you a breakdown and show you which GPU kernels were executed. But here, the main thing to note is that we've selected the time step loop. We can zoom in just to focus on that. Here, we're seeing in a little bit more detail just the 301 time steps. We can also identify here that there was a period where there was some disruption of the computation. This is something that varied from run to run based on other things that were happening on the network, for example. So we wanted to avoid that part and just focus on one of the other time steps where we can see more clearly what's happening there. So I'm going to choose one from early on in the computation. I don't know exactly which number it is, but here we're seeing just a single time step, and we're seeing a single threaded execution. So in this case, the pressure solve is executed serially. That means that it executes the first part, it executes the Schwarz part, and then it executes the coarse grid part, one after the other on the same thread. The threads are not used at any other points, or OpenMP isn't used at any other point, so that's the only potential part that would speed up from the use of OpenMP. We zoom in further, again, we can see a bit more clearly. The first part is the Schwarz computation, the coarse grid computation. They're both doing MPI communication, which is the red parts and the arrows here, and they're both launching CUDA kernels, which we perhaps see more clearly from the graph at the top here. We're also seeing the collective communication here, so these are all reduces where information is being exchanged after each of the phases of computation here. How does the multi-threaded execution change? Well, instead of executing those 2 parts of the solve one after the other, we see in the graph on the right the same execution but with 2 threads. So one thread executes the Schwarz and then is in a delay. At the end of the loop, it has to wait before continuing, whereas the other one is doing the longer computation that means that the first one has to wait. If you compare the 2 times here, the one on the right is slightly faster. It's not a huge improvement. And part of the reason for that is because that both of these threads are now competing. Not only are they both launching kernels, which is competing for the GPU, but they're both launching kernels. They're both doing MPI communication, competing for the network interface. So the benefits of using 2 cores and having 2 threads running in parallel, but having contention and sharing of the shared resource here is actually not paying off. And it specifically doesn't pay off because a lot of the computation which is outside of this parallel region is typically slower as well, because you no longer have the same data locality when you're going in and out of the parallel region, and the data is updated on one thread but then has to be shared with the other. So that was our understanding of how the single-threaded versus the dual-threaded execution in this case didn't actually pay off. It may pay off in other circumstances where there's more computation, but generally only a small part of the execution was able to benefit from the multi-threading here, and the benefits resulting from that when you have contention for shared resources were far from convincing. This is just the same picture zooming into the same thing, showing the pressure solve in much more detail. So we have a lot of information from the profiles going down and looking at what's happening in the threads as well, the execution traces as well, by examining what's happening on multiple threads. So those are the sorts of things that we'll see more of in the presentations from my colleague tomorrow. I think that's my time up, and I'll hand over to Cedric for the final presentation of this showcase.
Okay, so let me share my slides. So I hope you can see my slides.
Not yet, but I think they're coming. Okay.
No.
No, still not?
Now it's good.
Okay, great, thank you. Okay, so good afternoon. My name is Cedric Valency. I'm an expert engineer at the University of Versailles. So I will present now some examples of some of the information that Macao allowed us to retrieve during some assessments as part of the POP theory. So in a nutshell, Macao, which I will present more in detail tomorrow, is the performance analysis framework that we have been developing at the University of Versailles since in 20 years, basically. Mostly it relies on sampling to profile the application and then perform some advanced static binary analysis to identify exactly what kind of transformations were made by the compiler and then find the structure of the assembly code. So we tend to focus with Macao on obtaining the maximum performance available, mostly at the core level and node level. So making sure that, for instance, we're using the best capabilities of the processor. And we provide reports in HTML formats that are either, we can either provide some high-level metrics that will characterize the whole application, and we have more advanced reports that will focus, for instance, on the specific performance inside the loop and how to improve it. And it's also possible with Macao to perform multiple execution of a single application and compare them together and derive some metrics on that. So I will present multiple examples taken from multiple different code analyses. So this first one was OpenRadius. So Macao can provide some high-level metrics that characterize the whole application. So for instance, we can provide well, of course, the execution time, but also the time of the longest thread. And if we compare those, for instance, we can identify right away that there is some issue, probably because this means that some of the threads were running inactive for some time. And we can complement that with these additional metrics that provide a ratio of the average time during which threads are active. So for instance, here we could see that threads were active, for instance, for only 2/3 of the time. And we were running, for instance, we were using 96 threads, and on average, only 64 threads were running at a given time. So this allowed us right from the start to identify that there were some activity issue and on the application. Next, we can also have, these are all taken from the global view of Macao. We have some additional views that focus at the loop and function level. But here, right away, we could also see, for instance, so we can also provide a breakdown on the time spent in various categories of code, be it the application itself, or for instance, MPI runtime, OpenAP runtime, math functions, and the like. And so here, we can see that we spend nearly half of the time in OpenMP, in the OpenMP runtime. And another type of metric that Macao provides is potential speedups. Basically, these are the speedup, an optimistic speedup that we could hope to achieve at the application level if a given optimization was made. So here, for instance, this 2.1 assume that we spent no time at all in parallel runtimes and that we had a perfect load distribution. And we have rather important speed up because we can, for instance, have a 2 times speed up if we manage to achieve perfect load distribution and the perfect very little time spent in the parallel runtime. So this confirms that there is the issues that we observed that in the first stage were due to issues in parallelization. And going down further, we can see, so this is the function profiling view of the application, where we can see time spent in the function, and we can see that the hottest functions are actually all function from the OpenMP runtime. We were spending nearly half of the time in OpenMP runtime. And then from that, it is possible to find the origin of given functions. For instance, here, this provides the call chain, basically all the points from which the wait function that we can see, these are waiting function for OpenMP, we can see where they originate from. And they all trace back to this function. And we identified that there was a critical sections and some locks that were not correctly used, and then that were preventing some of the parallelization to occur efficiently. In this second example, this was a quantum chemistry code. So we have, I talked about Macao being able to run multiple analysis and then provide some global reports on that. So we have the stability mode, which simply tries to identify the stability of the application by running it multiple times and see how the time evolves. So here we are able to identify that there were some very strong variations from one run to the other, because here we have the time in seconds, it's in thousands. So we have very, very important differences. So most of the time, this means that there is some issue in the application. In this time, this was actually due to the application itself. There was some insynchronicity in the code and some random generation. But what we could observe by deriving some statistics on the functions from this stability report was that we had overall the same order of functions. The topmost functions were the same. So we simply needed after that to perform multiple runs to balance, to obtain an average of the timings we obtained. But on the whole, this meant we could trust the order of function that were provided by the profiling, even if the actual times may vary from one to the other. And after that, so this is a graph that comes with the thread activity ratio, the global metrics that I showed earlier. And here, for instance, this shows the activity of the threads over the execution of the application. So this was the serialization phase, but after that, we could identify that there is, so this is where the computation starts, but there is this first step where we have a very low thread activity because we are only out of 192 threads. We had only something like 20 threads running. So this showed some important, there was some load imbalance in this first step of the application. Another point that we could have from this application, Macao is also able to observe what the compiler did, and this implies also checking which compiler flags were provided to the compiler, because compilation flags are very important. And for instance, in that case, we could see at the function level, it's possible to have different compilation flags depending on how the compilation is performed. We can have different compilation flags for functions. And so in this case, it was rather glaring that all the functions had all the compilation flags. So these are the specialization flags, for instance, that will allow the compiler to know on which platform the code will be running so that it can adapt the code correspondingly to take best advantage of the core features. And here, this was this comparison function, which due to how the compilation was done, had completely different flags. And in fact, it had only a generic specialization flag. So the compiler was not able to perform any optimization on that particular function. So after that, we could provide this information and the compilation process could be updated so that this function, which was taking nearly 10% of the execution time, this function was after that could properly be optimized. And I have a last example of code. So this was a code that existed in two versions, in C and Fortran code. And so this time we were able to run both analyses on this code and compare them. And the comparison showed that there was a significant difference between the C version and the Fortran version. And moreover, the categorization showed that actually all the difference was due to memory functions. So using the comparison mode as down to the function level, so it's possible when we compare code like that to have a comparison for each function. So here, these two functions are actually the same one, but they happen to have a different name. So we could not automatically match them, but we know they are the same ones. But otherwise, most of the other functions could be matched, and we found that one actually, which was a memory set function that was added by the C Intel compiler that has no equivalent in the Fortran version, and that was the one that accounted for the difference we observed between the timings of the two versions of code, and this allowed us to identify and fix that. And with that, I'm a bit early, but maybe I was a bit fast. But anyway, I'm finished for what I presented, and tomorrow I will present more in detail Macao and what it can do.
Okay, thank you, Cedric. So